Thank you for having us today. So I'm Kerry Klemmer. I'm a postdoc working with Mike, and I will be presenting on the forward UQ portion of this talk, so forward uncertainty quantification for robust wind farm design and control. Okay, and so the motivation for this work lies in the fact that wind farm control often relies on models, and these models require wind condition inputs, and these can be things like wind speed, wind direction, and turbulence intensity, which we'll focus on in this work. And these inputs have inherent uncertainties about them, and there are many different sources of uncertainty, and the two that I'll focus on here are the source of the wind condition input data. So we can have in situ measurements, we can have non-in situ measurements, we can have numerical weather prediction, and we can also have turbine measurements. So there are a lot of different sources of data, and we need to kind of consider any uncertainties that are inherent to these sources. And then additionally, another source of uncertainty is the level of description. And so what I mean by this is that kind of here, we're thinking about different quantities and what happens if I use a quantity that is aggregated over, let's say, an entire year versus a more instantaneous version of that quantity. So here we're talking about turbulence intensity and whether we use a median value over a year or something that's averaged over a shorter window. And so the goal in this work is to quantify uncertainty in predictions of these aggregated metrics, such as annual energy production and farm efficiency, owing to uncertainty in these two sources. So the source of the wind condition input data and the level of description, specifically in the turbulence intensity. And so in order to do this work, we've looked at one particular wind farm. So that is the Vineyard Wind 1 farm, which I'm showing on this map. We have Martha's Vineyard, and then the farm is shown here with the white dots for the turbines. And so this is the first commercial scale offshore wind farm in the United States, and it has 62 GE 13 megawatt turbines. And so for this study, we have two different sources of data. We have LIDAR and we have numerical weather prediction. And so the LIDAR is shown with this blue square, and it's located 25 kilometers from the farm. So these are high fidelity measurements, but they're not in situ measurements. And then the numerical weather prediction, we have two different sites, but I'm going to focus on the one that's within the farm for this presentation. So we have one site that's located within the farm and then one that's located, co-located with the LIDAR. And so the numerical weather prediction data introduces uncertainty through modeling assumptions that are going to be inherent to these models. And then the LIDAR data, as I've said, is not in situ. And so this also is going to introduce some uncertainty when we're trying to think about input conditions to our wind farm. Okay, so just a brief outline of the rest of my talk. I'm going to go into a little bit a comparison of the wind conditions that we see with these two different sources, so the LIDAR and the numerical weather prediction at the VW1 site. Then I'll talk about the forward UQ framework that we've used in this work, and I'll get into the results following that. So for our two different sources of uncertainty that I've mentioned. So starting with the comparison of the wind conditions. So first we're going to look at wind speed. And so this is a contour of wind speed over a year. So this is just one example year, 2017, as a function of height above ground level. And so kind of largely, obviously, again, these are not co-located, but, you know, we see similar regions of high wind speed and similar regions of low wind speed. So there is kind of relative qualitative agreement between these. And then when we look at something like turbulence intensity, we actually see something kind of a little bit different. There's maybe less agreement. And there's some kind of key differences that come from the modeling assumptions inherent in the numerical weather prediction. So namely, what we find is that we have increasing turbulence intensity as a function of height, and same for turbulent kinetic energy, which I'm not showing here, but these are related. And so we see this in the LIDAR, but we don't see this in the numerical weather prediction. And so we've done a bit of analysis on this, and what we found is that these trends seem to be tied to seasonal stability patterns, which are not adequately captured by the planetary boundary layer model in the numerical weather prediction, or at least the variation with height is not captured. So as we can kind of see, the red is indicative of unstable conditions and blue is indicative of stable conditions in these color bars at the bottom. And so when we have more stable conditions or kind of leaning towards neutral, which are these lighter or white colors, we see stronger increases with height. And then when we have very strong unstable conditions, we really don't see this. And so we've tied this kind of to the stability, which again, the numerical weather prediction has trouble capturing, particularly for these very stable conditions. So this is just to give a sense of kind of the differences between these two sources of data. So now I'm going to move on to how we've actually done this forward UQ. Okay, so starting with the wind condition input data source uncertainty. So for this, we have our two sites. So again, I'm showing the map here. The LiDAR is located just off the coast of Martha's Vineyard, and we have distributions for wind speed, turbulence intensity, and wind direction. And we have the same thing for the numerical weather prediction. And then we run these through our model, which here we're using Flores, we're using Gaussian wake model with sum of squares free stream superposition, and we have a wake added turbulence model as well. And then with this, we're able to get measurements or predictions, excuse me, of farm power, and we can aggregate these to get metrics such as AEP and farm efficiency, and we can intercompare our two sources, which I'm showing here. And with this, we can then get a measure of kind of the error or the uncertainty with like a percent difference, which is what I'm showing in these two plots. And so then for the turbulence intensity uncertainty, we can do the same thing, and we can do it for both our sources of data, but here, as an example, I'm just showing for the LiDAR. So here we have our full distribution of TI. And then for comparison, what we do is we use median TI, which I'm showing here with this dashed black line. And so then using this, we again run this through our wind farm model. And as output, we again get these comparisons of the AEP calculated with the full distribution versus AEP calculated with median, and same for farm efficiency. And we can also look at percent error. Okay, so now I'm going to quickly move on to the results. So starting with what we see for the turbulence intensity. So for the next few slides, I'm going to show plots that look like this, where we have data that's aggregated over 3 years, 2017, 2018, and 2020. And this is based on the availability of the LiDAR data. And then these gray regions are showing interannual variability. So we want to compare the errors that we see to interannual variability to kind of see if it falls outside of it or within it. And so here, the error bars, which you can see more clearly in the numerical weather prediction plot, are absolute error in TI. And so the key takeaway for turbulence intensity uncertainty as it propagates to AEP is that we don't find that it ever exceeds interannual variability. And so this assumption that we've made of using a median value of TI over one whole year actually is not such a bad assumption when we look at a metric like AEP. And then for farm efficiency, kind of showing the same thing now, but we find is that turbulence intensity does exceed interannual variability when we're away from hub height, mostly for the LiDAR data. So turbulence does have more of an effect, we know, on the wake and on kind of replenishing the wake, which will affect farm efficiency. And so it does have more of an effect than we saw as compared with AEP, at least as compared to interannual variability. And so as I said, this uncertainty has kind of a limited effect on this aggregated metric of AEP, which is what's shown here. So we can see the percent error, and it's all less than 1%, where this dash gray line represents hub height for our turbine. But what we can do is look at the uncertainty that's present when we actually look at a different metric, such as instantaneous farm power. So now taking the farm power that we get from each of our different wind condition inputs and comparing that to what we would get if we used the median value for TI. And we can see that there's a much greater error that we find. So this is the root mean square error in farm power as a percentage of the mean farm power. And these errors are now ranging from 3 to 4%. And this is going to be important in a wind farm control context, again, because here we're thinking about a more instantaneous metric. And kind of just to put some numbers to it, this 3% error at hub height corresponds to the power needed for roughly 12,000 homes. So it does have a significant effect in the context of thinking about farm power as opposed to AEP. So now I'm going to go to this last part and talk about the results we have when we look at the wind condition input data source uncertainty. So again, we have these plots. And here the error bars are the data source uncertainty percent difference. And so our key takeaway is that the wind condition input data source uncertainty actually exceeds interannual variability at most heights across the rotor when we are below hub height. And so this comes from also the fact that the data source percent difference predominantly is decreasing with increasing height. Which was an interesting trend that we saw that I will get into a little bit later. But overall, this data source uncertainty does have a significant effect on AEP. And then looking at farm efficiency, the wind condition input data source uncertainty exceeds interannual variability when we are away from hub height. So again, data source uncertainty does have a significant effect. And we also kind of see an interesting trend with height here. And so we were interested in kind of looking at why these trends emerge between these two data sources. And so the way we went about this was kind of in 2 steps. So the first step was to do a sensitivity analysis. And so with this, we ran these tests where we would hold one of our input variables fixed and allow the other 2 to vary. And so in the top row, we have where we're holding wind speed fixed. In this row, we have turbulence intensity being held fixed, and in this row, wind direction. And so for each of each point along this curve, that represents one value of wind direction, for example, that we allowed the other variables to vary and then aggregated over that. And so what we find, looking first at AEP, is that AEP is most sensitive to changes in wind speed. So, we go from 0 to 8,000 gigawatt hours, which is a huge change, and we don't see the same range over wind direction or turbulence intensity. So kind of unsurprisingly, AEP is very sensitive to these changes in wind speed. Farm efficiency is a little more complicated. It does show sensitivity to all 3 variables. And the clearest trends are really visible when we look at wind speed and TI. So we do have this region where farm efficiency is insensitive to wind speed. And so in these regions, we might expect that turbulence intensity and wind direction might matter more. And so with these sensitivity tests in mind, we can now look at how the distributions, specifically for wind speed and turbulence intensity, are changing as a function of height between our 2 data sources. So here I'm showing 60 meters, 140 meters, and 200 meters, and 60 meters was our minimum height, and 200 meters was our maximum height. And so for wind speed, I think it's pretty clear we see that these distributions are converging with increasing height. And with TI, it's slightly less clear, but it's possible that they seem to be diverging. And so what we can do is we can look at variation in the statistics with height to kind of dig into this a little bit more and see if kind of what we're seeing qualitatively is actually happening. So starting with wind speed, and again, wind speed will be particularly important for AEP, which I'm showing in the corner. And as we can see, the AEP predictions for these 2 sources is converging with height. And so here I'm showing mean wind speed, median wind speed, and the standard deviation in wind speed as a function of height. And we see that these statistics are primarily converging with height. And so coupled with that sensitivity analysis, this convergence helps to explain the trends of decreasing AEP error with height. And then we can do the same thing looking at turbulence intensity. And so again, this will be important for farm efficiency, where we see this kind of converging and then diverging behavior. And so we see something similar in TI, particularly looking at the mean and the median, where the TI statistics converge and then seem to diverge as we move away from hub height. And so as we've kind of said, farm efficiency is sensitive to TI, and so it's going to be sensitive to this diverging TI behavior, particularly as we see that the wind speeds are converging, but we don't see this the converging behavior mimicked in the farm efficiency. So we believe this is in large part due to turbulence intensity. Okay, and so to conclude, what we've found in this work doing forward uncertainty quantification is that this wind condition input data source uncertainty significantly contributes to uncertainty in AEP. We saw the largest uncertainties kind of in this pairing. And TI uncertainty did not have such a large effect on AEP, but we did see that it had a measurable effect on this instantaneous farm power. And so, as I said, this is going to be important in a control context. And so kind of the next step for what we're looking at is improved wake model, wake turbulence modeling, and also along with this model form uncertainty quantification. And so kind of the motivation for this next work, in addition to the present work, is that we know that turbulence intensity has a very large effect on replenishing the wake, which is what's being shown here. And so with this, we plan to use large eddy simulation of wakes, as shown here, to kind of analyze more of this problem and dig into some of the flow physics so that we can come up with improved models. So thank you, and I guess I will give it to Mike.
Great. Unless there's any quick technical questions, we can pause for that now. Otherwise, I can keep going, and we can also have a longer Q&A at the end. But were there any quick questions? I see Nathan has a question. Go ahead, Nathan.
I have a question. I'm not sure if I understood the analysis you did correctly, but if I did, it looked like you were treating each of the uncertainties as independent variables. Did you consider any correlation between wind speed and turbulence intensity or wind direction? And how would that influence these results?
So I guess in the data source uncertainty, they are all considered together. They are all interrelated. So they aren't really independent variables as a result. I think with the TI uncertainty in kind of trying to separate that out, that was mostly about looking at something that is a common practice in the field of using a median value. And so I guess that's kind of separating out one particular assumption that is made. But with the data source uncertainty, I would say that it is treating all of these variables together and kind of lumping them into whether we're looking at high fidelity measurements or numerical data, but maybe then not necessarily digging into the deeper assumptions in the numerics or in the models of the numerical data. Does that make sense? Answer your question?
Okay, thanks. Yeah.
Yeah, they're fed in as a joint distribution over those three variables rather than taking the variables independently in three
that makes sense.
distributions. Perfect. Any other quick questions before we continue on? All right, great. So let's see. I also don't use Teams that much, but hopefully it's shared now. And I've lost ability to see anyone, so can someone tell me if it's shared verbally?
Yep. Yeah.
Okay,
good.
Great. Yeah, so I'll continue right on where Kerry left off. So yeah, this is the high-level picture that I like to present in terms of how we're in our lab group viewing the wind farm flow control problem, and really the exercise in terms of modeling wind farm flow for decision making, such as wind farm control, but also for siting and design, relates to two primary exercises. The first is appropriate models of the atmospheric ground layer inflow. Here I've just sketched one with a little jet. It doesn't have to have one, of course, but the primary questions are how do wind speed, wind direction, turbulence, stability, and other key meteorological variables vary in the atmospheric boundary layer as it then will impact the wind farm. And that's been the focus of Kerry's discussion so far. But then the second exercise is our modeling ability to predict the wind farm flow. And the wind farm flow, of course, depends on the incident atmospheric ground layer flow, among other details of the wind farm geometry, the turbine control strategy, and so on. And so really the exercise of predicting then the control strategy, which is going to maximize some metric we care about, whether it be power production or loads or anything else, really relies on predicting turbine power production in the context of the atmospheric ground layer flow, the wake interactions and other features of wind farm flow physics, and then the power production of the wake turbines in the context of the wake interactions. So Kerry spoke about this first bullet, and so in the second part of this talk, I'll speak more about uncertainty quantification related to the wind farm flow. And so the key that we're going to focus on here is that essentially simplified engineering wake models that are used for wind farm flow control inherently parameterize turbulence with a wake spreading rate. And they do this because to remain computationally tractable, it's challenging to resolve all the relevant energetic length and time scales. And so these models are parameterizing turbulence typically with a wake spreading rate. Not every model is doing this exactly the same way. There's a spectrum of models. Of course, one could use all the way from linearized RANs down to a very simple Jensen style model, but fundamentally they're parameterizing turbulence in some way. And so just to give you a sense of what this looks like in a little bit more detail, and I won't go too much into the specific modeling details here other than showing you where this comes from. An initial approach, of course, to model wake interactions could be something like a Jensen model, where you take these assumptions listed on the left-hand side, statistically steady, linearize the advection term, neglect viscous, pressure gradient, Coriolis forces, and then you assume that the wake is spreading linearly based on either empirical results or some simplified derivation from momentum equations. And then what you get is that the linearized momentum conservation gives you that the defect momentum flux is conserved. Okay, so that's what it is in words. Here it is in equations. What you essentially have is that this defect momentum flux here listed on this left-hand side, which depends on this wake velocity u, which is defined here, so the deficit with respect to the free stream, and this wake area, you can see pi over 4 wake diameter squared. Both of those depend on x, but they're equal to a constant. And so that then gives us, okay, that the wake is going to recover with the inverse of the wake diameter squared. So it's recovering with the spreading of the wake area. And so in a Jensen framework, what this looks like is then to just say, okay, use inviscid momentum theory, or the kind of analysis that gives you the Betz limit as an initial condition to give you this initial velocity deficit delta u naught, and then we prescribe a wake diameter. And so that goes in the denominator, and then we square it. And so this is that wake diameter as it's spreading, and it's squared here. And the primary thing that we can see is that we've assumed that the wake is spreading linearly, and that it's parameterized by this wake spreading rate, k star. And the primary point is that this wake spreading rate is an unknown input to this model. And it has to be prescribed in order for this to be a fully predictive model. So something that you can then use to make decisions about wind farm layout or wind farm control. So that's what it looks like in a Jensen context. It's very similar in more advanced models, for example, in the Gaussian wake model. So Bostanka and Porté-Gel, of course, proposed the well-known Gaussian wake model form in 2014. And really, you can see it has almost the same kind of heritage. It really depends on this denominator here and on this left-hand side here of this sigma y and z here. And if you just take an initial assumption that those are the same, of course, you could spread them out and have more parameters, but just for this talk, let's set them equal to each other. This is the wake spreading essentially in the y and the z direction respectively. Then we have that the wake is also spreading linearly, and it is dictated again by this k star. And so the primary point that I'm trying to say here is that essentially we need to prescribe this wake spreading rate in order to have a fully predictive wake model. And the initial approach for estimating this parameter of k star has been to take an empirical modeling framework where we can essentially use idealized large eddy simulations to tune a model for k star based on assumptions that k star depends on key meteorological variables in the atmosphere. So for example, in the model proposed by Niafar and Porté-Gel, they presume that K star depends on the streamwise turbulence intensity, using a similar framework to what Kerry was just discussing. And this is exactly how that dependence on the turbulence intensity directly comes into a Gaussian type wake model, as implemented in what she was discussing. And so here you can see, okay, that they tuned a model to fit the idealized large eddy simulations that they had, which were the primary use cases were pointed out in the study, mostly related to assumptions of neutral atmospheric boundary layer and a limited range of streamwise turbulence intensity. So within this, stability and other effects are explicitly neglected. Another framework, which we may propose here, is instead of using an empirical model which relates K star directly to the turbulence intensity, is to approach this as a data-driven modeling problem, where really just in a high-level framework, you can say, okay, our goal is instead to minimize the data space objective function, where we have some data y, so some observations, which I haven't defined yet, but I will later. We have some model G, which could be a wake model. So G could represent this modeling to predict delta U. And the wake model depends on unknown parameters theta, where in this particular wake model, we're going to focus on theta being equal to K star. And so then the goal of data-driven modeling or calibration to automate this process is then, for example, as one objective function could be to predict theta star, so the best parameters theta, which gives you the minimum of this data space objective function. So in the context of how this relates to previous work, of course, there's been a long list of authors and doing very important work in wind farm flow control, where they note that it's important first, before applying these simplified engineering wake models in a new context, to perform tuning to offline data. So this is not, of course, a complete list of authors who have done this. It's very common to tune the model parameters using, for example, large eddy simulation or available data to improve the predictive capabilities in a new wind farm context. But the primary challenge with this kind of hand tuning exercise to the specific use case is that for generalizability, wake model parameters really depend on a high dimensional set of conditions. They depend on site and also time specific conditions. So for example, the wake model parameters, this wake spreading rate, is dictated by, for example, the local turbulence and shear that a wind turbine sees, depending on the geometry of the wind farm, the layout, et cetera, and also the stability. And so this is challenging to handle in a manual tuning process. And so a parallel approach would be to directly optimize the parameters using observational data. So what can that look like? Again, we pose this here as a minimization of the data space objective function. So the same thing I showed in the previous slide. But essentially, the way we think about it is to optimize model parameters for each independent value of wind speed, wind direction, and turbulence intensity as an initial approach. So we can take historical data from a wind farm that we may be interested in and separate the observational data, the power production data, into sorted, associated based on the wind speed, the wind direction, and the turbulence intensity incident to that farm. And then using those data, the power production data from the turbines, as our array y, we can then find the parameters that minimize the data space objective function listed here. And so this is exactly the approach that we have taken in our previous study, where our goal was to essentially assess the predictive accuracy of our wind farm flow control model with this kind of automated parameter calibration approach. So the full detail of the wind farm flow control model is listed in the supplement of this paper here. Essentially, it's a Gaussian wake model with a power production model for wind turbines and yaw, which also depends on wind speed and direction shear and so on. So the full details are in the paper. But the primary point that I want to say is that our first exercise was really to validate the approach that I just mentioned, where we fit model parameters we calibrate model parameters based on wind speed, wind direction, and turbulence intensity in an offline sense. And so this is really towards the generation of a lookup table in an open loop wind farm control framework. So then we can do that all offline using only historical data. That gives us parameters for each independent set of wind speed, wind direction, and turbulence intensity. And then we can then apply those in a predictive sense. And so to validate this approach, we then had to generate data which is out of sample of the historical data from the operation of the farm. And so to do that, we measured wind farm power production depending on the yaw misalignment of turbine 1. So this is the layout of the farm. We're mostly focused on wind conditions for flow coming from the north. And we yaw misaligned turbine 1 from minus 25 degrees to plus 25 degrees, where we held each one for approximately 1 hour and performed the experiment for about 3 months. And we have this reference turbine here. And so the way we're going to validate this approach, this parameter calibration, based on these 3 wind conditions, is then we can look at the same wind conditions, assume that the wake model parameters don't depend on yaw, which is an assumption, and then to predict out of sample what is the power production associated with yaw misalignment instead, which the calibration, the automated calibration, hasn't seen. And so, for example, if we look at wind conditions coming directly from the north, so this is the same as this array here, but now I've rotated it, so flow is from left to right, and each turbine is in standard controlled. So this is sort of the calibration data, the historical operation data, if you want to think about it that way. Then each turbine is in yaw alignment, generating wake, and there's wake interactions for those downwind turbines. The power production data from the SCADA is shown in the lines, and the power production data from the model is shown in the dots. But the agreement here is in large part from the fact that we're learning the parameters that minimize that data space objective function. So this is really a calibration data set. Our goal is to predict the model parameters that minimize the error of the wake model for yaw misalignment equal to 0. So then we want to ask, how well does this model predict out of sample? So how well can we predict the power production based on not changing these parameters? So we hold fixed the model parameters, but then we change the yaw misalignment of the turbine in the field and in the model, and we ask how well our model can actually predict out of sample for yaw not equal to 0. And so that's what's shown in this red line instead. So to show a little bit very quickly, more generalized results, so I can get to the UQ part, because this has just been parameter optimization so far. We can generalize this and look at many wind conditions. That was just for one yaw misalignment. If we change the yaw misalignment of turbine 1 anywhere between minus 25 and plus 25 degrees, we can then compare our wake model predictions where our calibration only sees this point and is then predicting completely out of sample the power production for all of the other wind conditions. And we can see, okay, power production of the second turbine strongly depends on the yaw misalignment of the upwind turbine. For negative yaw misalignment, based on geometry, that reduces power production compared to standard control, whereas for a positive yaw misalignment, that increases power production. You could guess that from geometry, but it's nice that the model is able to well reproduce those trends. Then we can ask the question also for the 3 turbine array summed together, how well is our flow control model based on this calibration approach able to predict it? So we can see, okay, yes, there's a preferential different direction. So positive yaw misalignment is better for the 3 turbine power production than negative yaw misalignment. And we can also see that generally the model is predicting the same location that maximizes power production in the real field data for gamma. So that's a validation that our modeling framework is actually able to predict the true optimum control strategy to maximize power as a function of the yaw misalignment of the leading turbine in this array. So that was the primary exercise that we wanted to ask here, rather than just asking, can we increase power production when we do wake steering? The question is, can our models, based on this kind of calibration framework, predict the location of yaw misalignment that actually maximizes the power production, considering also many suboptimal yaw misalignment angles? So that was the primary result of this study. And then here, yeah, a 28% increase for these particular wind conditions. And this is just for one set of wind speeds and turbulence intensities. We can do this for any other one as well, which is detailed in the paper. Okay, so the full details are that, so this is just for one set. We predicted the optimum yaw to plus or minus 5 degrees for 4 out of the 6 wind direction cases. And then the wake model predictions are within the 95% confidence intervals of the field data for 46 out of 64 unique combinations of gamma and alpha, which is the wind direction, or sorry, the yaw misalignment and the wind direction respectively. Okay, so now getting to the UQ, here all I've shown you so far is, okay, we can calibrate the wake model parameters based on the field data. But if we really want to improve robust decision making, what we really want is a prediction with a confidence interval, because this will then allow us to select the control strategy, the wind farm flow control strategy that actually maximizes power under the uncertainty that we have. And the uncertainty could be as detailed by previous authors, for example, Eric looking at wind direction variability and so on, and yaw misalignment variability. But it could also be due to uncertainty associated with the wake model parameters themselves. And so to do that, we actually need to predict what are what is the probability distribution of the wake model parameters based on the observational data we have, rather than just predicting the maximum likelihood estimate, so the location that minimizes the data space error. So we generally state the relationship between model and data using this equation. So Y would be observational data. G, again, is our model. Here we've included model error delta, which we generally don't know, because if we knew it, we would put it back into the model. And then eta is measurement error here. And the key idea behind this equation and why this is normally distributed is that we assume that our finite averaged observations that we grab from the field, for example, are a noisy approximation to the infinite average, right? So we don't have access to the infinite average of the power production from a real practical field setting, because there's always some limitations, of course, in how long you can average. And so it's important to incorporate the uncertainty that translates then as a realization of measurement error, which we then say is normally distributed by the central limit theorem. And the primary mechanism that makes this work, that we can assume that the measurement error is normally distributed by the central limit theorem, is that the averaging timescale that we do pick from the field data sufficiently resolves the relevant energetic length and timescales. And I'm being a little cryptic about that because in practice, it does depend on the wind conditions, right? So if we have a steady or a stably stratified atmospheric boundary layer where turbulence is suppressed, that averaging timescale can come much further down to capture the relevant length and timescales compared to a convective boundary layer where length scales are larger. So I know I'm running out of time. I picked a hard stop, so I'm already going beyond it. But basically, then what we have to do is just construct a likelihood function. So for this normally distributed measurement error, then the likelihood can be just stated as this. You can see, okay, the data space error is here, and then sigma shows up here, which is the observational covariance. And so the likelihood of observing some data y, some data sample y, given some parameters theta, is proportional to this likelihood function. And then we can use Bayes' theorem to then say, okay, the posterior distribution of theta given a bunch of observations, m observations, is proportional to the prior measure that we have over theta. So what is our prior distribution that we're assuming for our parameters? And then the product of each essentially weighted data space error associated by the covariance from each of our samples m. Okay, so this is work done by Michael Locascio at Stanford, together with myself and with Catherine Gourlay. I'm going to skip through the technical details. There's a couple of technical challenges to solve. One is that the wake model parameters actually have to be constrained, but to do uncertainty quantification and sampling, it's much better to do this in an unconstrained space. So you have to develop a mapping between a physical space which is constrained, so the wake model parameters have certain bounds, such that you don't get nans and infs and so on in your model predictions. But then in the sampling space, they have to be unconstrained, and it's better to have a Gaussian prior and so on. So that's what this mapping is doing. And then in terms of the technical details of the MCMC algorithm that we sample from this, that we use to sample from this posterior distribution, we're using a random walk metropolis algorithm, which is essentially the simplest possible MCMC algorithm. So then the framework that we're using, and I'll just show a few results. This is pretty much the end. I know it shows lots of slides left, but most of them are sort of additional technical details if others were interested. We wanted to ask 3 research questions. 1, how does K star, when we're estimating it from MCMC, depend on the row in the wind farm? So how do the wake model parameters depend on which row you're in the wind farm? Is the estimated data-driven estimation for the wake model parameter different for a free stream turbine versus a wake turbine? We expect it physically, so it'll be interesting if we can recover that from a data-driven methodology. To what extent do K-star estimates differ between superposition methods, so different ways of superposing individual wakes together in a wind farm modeling framework? And then which superposition method also leads to lowest out-of-sample prediction error in the same kind of way, where we train based on yaw equals 0 and we predict out-of-sample for yaw not equal to 0? And we use 2 data sets to answer these questions. The reason why we use 2 data sets is that in large eddy simulation, we have the convenience of being able to exactly control our boundary conditions. So we can essentially ensure that this central limit theorem approximation is a reasonable one in large eddy simulation if we fix our boundary conditions. Whereas in the field setting, it's more challenging because aside from variations due to turbulence and finite sampling error, we also have boundary conditions, which are changing constantly as a function of time due to mesoscale variations and others in the atmosphere. So I'm going to skip through. Okay, we use LES to generate the data, but then here I'm just showing you that we can estimate these wake model parameters in a 5-turbine test case, which is shown here, based on assimilating data from the large eddy simulation. So the data Y is coming from large eddy simulation power production, and we're learning the wake model parameters and their probability distributions based on this Gaussian wake model. And what we can see is a few things. One is that, okay, these are the 5 different wake superposition methodologies that we considered in this study. We can see that the wake model parameters estimated by the data-driven approach do depend on the superposition methodology, which is an elucidation to some extent of model error, which I can talk more about in the Q&A if you're interested. We can also see that as we go further downwind in the farm, the wake model parameters increase. So that tells us this is the same kind of interpretation that as we have wake added turbulence in the wind farm, that will increase TI, which will also increase the wake spreading rate and increase the recovery time. So this is the same kind of intuition that we can see recovered in the data-driven approach. But we also see kind of plateauing behavior. As you go further downwind, the deviations between the mean K-star values starts to get smaller and smaller, which is another interesting result. So it's trending towards some kind of infinite wind farm behavior eventually. Of course, there's a small wind farm considered here. And then the lines here are estimates where we're using the standard K-star predictions based on turbulence intensity alone. So pretty much, yeah, that's the main few things I wanted to say, that we can estimate these probability distributions. And then the other thing I just wanted to say, okay, using our field data set, is that we can then do the same thing that I did using the wake steering experiment, where we learn our parameters based on yaw equals 0, and then we use that to predict out of sample for yaw not equal to 0. And so that's what we're doing here, okay, from the field data set, which is a different wind farm. We learn our parameters for each superposition methodology for yaw equal to 0, and then we feed in this distribution of parameters, which then gives us essentially a stochastic wake model. So it allows us to predict the probability distribution also of the power production. And so that's what we do here. We're now, okay, comparing the field data, which is shown in the dashed lines, to the predictions out of sample, which are shown in the colored distributions. This is what the distribution of power production, which now comes with an uncertainty estimate, uncertainty under wake model parameter uncertainty. And if we aggregate all of these superposition methodologies and we compare their error, the data-driven for turbine 2, this is the empirical approach for turbine 2, data-driven for turbine 3, and empirical approach for turbine 3. On average, the data-driven methodology reduces out-of-sample prediction error, but especially for what we generally consider are the best superposition methodologies in the sense that they're most physically motivated, especially the Zhang and the NIFR methodology for wake superposition. The very last thing I say, okay, I know I'm going long, I always do it. Apologies. The very last thing I'll say is that, okay, then now we have an estimate of the uncertainty of the wake model parameters, is then we can do an optimization under model parameter uncertainty following previous studies that have considered this kind of robust optimization for wind farm flow control. So the exercise, instead of picking gamma star, the yaw misalignment set points that maximize power production, we can then just pick the yaw misalignments that maximize the expected value of the power production subject to uncertainty in the wind conditions, shown as this probability distribution C, and the uncertainty in the wake model parameters theta. And so that's something that we can also do. So I'll pretty much just stop here and take any questions. I know that was a bit of a whirlwind, but yeah, happy to continue the discussion, and then we can switch over to the other things we need to get to, Eric.
Yeah, thank you so much, Mike and Kerry, for super interesting talks there. Yeah, so we probably have like 5 minutes for questions if anyone has any questions.
Yeah, yeah. Just wondering if you've thought, Mike, if you've thought about how to include so not the parameter uncertainty, but the model form uncertainty or whatever in this optimization under uncertainty framework.
Mm-hmm. Yeah, I think that's the logical next step. We've thought a little bit about it. I think the naivest possible way would be to start with saying that model form uncertainty is in some sense captured by choices in modeling like superposition and things like this. This approach can be interesting. One way to improve that is that in some sense we have a good idea of which superposition methodologies are sort of more physically justified than others. So in a way, it's kind of like intentionally making your model worse, but calling that model error. So that's one starting point. An approach that I'm more interested in doing, which we haven't started yet, but I'd like to, is to try and more directly confront the modeling error question using data-driven methodologies, for example, using machine learning techniques to directly learn modeling error, where the primary exercise is how you orthogonalize learning of model parameters, which are physically motivated and modeling error. So that's a more technical exercise, which I think would be probably the more promising direction. But those are just initial thoughts. Kerry, any ideas? Kerry's done much more work on model form uncertainty.
Yeah, so with the Vineyard Wind 1 project, we've talked a little bit. We've started doing kind of the modular, changing the superposition model, but then also talked a little bit about using kind of like sensitivity analysis methods that use like grouped Sobel indices effectively. And yeah, basically I have seen work on this for other applications, but if we could kind of, you'd have to use some physical intuition for these models. So for example, the superposition models, but if you can define some kind of like blending parameter between them, then as opposed to getting kind of discrete, modular, using this model, you can have a more a distribution effectively. And so that is something that we have talked about and I think might try to do in the future, kind of as an add-on to the Vineyard Wind 1 project, since we've looked at now the input uncertainty, and we can kind of, with the Sobel indices analysis, tack on parameter uncertainty and model form uncertainty to try to kind of simultaneously address those three pieces, which are, as Mike pointed out, obviously very key to this problem.
Excellent, thank you. And yeah, Kerry, also wondering the Vineyard Wind case study you presented, if you're also looking at wind farm control, how the TI or the wind condition uncertainty impacts the uplift in AEP, for example.
So I am personally not a controls person. I'm coming from a turbulence modeling background and uncertainty quantification, so more on the model form side. So I cannot really confidently speak to wind farm control, but maybe Mike can take that.
Yeah, I think we should do it. Yeah. So we haven't done it, but we should do it. Yeah. I think it's alluded to in future work, but I think that's a clear next step in terms of seeing to what extent the uplift is statistically significantly affected or not by these kinds of uncertainty. So that's a great question. Yeah.
Okay, good. Yeah, because I think especially the uncertainty in TI could have a big impact on how well wake steering works for a site.
Yeah,
All right.
exactly. That was one of the, yeah, exactly. One of the primary motivations, yeah, to study that problem. Yeah, exactly.